Hey everyone, Mr. Fritz here. Let's talk about Venn diagrams and let's talk about proving independence. First off, Venn diagrams. Let's talk about what a Venn diagram is. A lot of you have seen what these are before, but let's just get a little refresher. So imagine I had this little circle to illustrate some characteristics of cats. Cats have fur, they say meow, they have paws, they're mostly independent, and they have whiskers. If I were to compare or comprise a list of characteristics about dogs, I could say they have fur, they say woof, they have paws, they're pretty dependent, and they have whiskers. So how could I illustrate both of these things? How could I illustrate these two together and visualize these shared traits together? If I wanted to make a nice chart that shows all of the characteristics of both of these things and account for what's shared, I could use a Venn diagram. And basically what I do in a Venn diagram is I can compare sets of information and also display where the sets might overlap with one another. So things like fur, whiskers, and paws, they exist between both of these independent groups. So they exist in groups of dogs and they exist in groups of cats. So using these Venn diagrams, it's a nice way to quickly, efficiently illustrate things that are traits that are shared as well as traits that are not shared between two groups of things. So let's see another example. Let's talk about numbers now. Here I have this rectangle, and this is considered to be my sample space. And this rectangle is comprised of whole numbers that are less than 13. So right now they're just kind of floating around in this rectangle, in this sample space. But let's say I wanted to group them together. I wanted to corral a bunch of these to follow a certain rule. Let's get all the even numbers together. Well, I'd say I'd grab all of my even numbers and I would put them in this even section. Now let's say I wanted to find another way to corral or round up some of these numbers. And let's use this multiple of 3 rule. So let's find all the values that are multiples of 3 in this sample space. So right now, everything that's not already inside of that red circle is going to be a 3 and a 9. And so right now I've kind of, if you imagine these as like walls or borders or barriers, everything has kind of been fit into circles. But we have a little bit of an issue with what's going on here because I do have some values in the even circle that is also a multiple of 3. So it should really exist in both of these sets. It would be inefficient for me to rewrite a 6 and a 12 here. I'd like a way to demonstrate that they're shared between the two sets or the two different rules. So what I do is I kind of merge, I shove these circles together, and where they overlap is where they exist in both of these sets. So I can get all kinds of information from this diagram. If I look at all the whole numbers that are less than 13, I can see which ones are even quickly, I can see which ones are multiples of 3 quickly, and I can see all the ones that do not fit either of those characteristics, the 1, the 5, the 8, the 11, and the 7. So let's talk some terms about what we've been throwing out here. The thing that is in the entire rectangle, that is called the sample space, and it's enclosed in the rectangle. One thing to note is that it's not, it's everything within the rectangle, and all the circles and all the Venn diagram circles are inside of this rectangle, so they're also contained in the sample space. So just because 2, 6, 4, 10, and 12 are in the circle does not mean that it's not a part of the sample space. All of this is containing the sample space. Whatever is in this circle is considered the event A. So this could be the event that a number is even. It could be the event that it is going to rain. It could be an event that students are taking pre-calculus or whatever. It doesn't really matter what it is. Everything outside of that circle is representing the event not occurring, or what we'd call not A, with this notation A with the apostrophe here. So it's basically just the complement of that A, that event A, and it's in this case it would be 1, 3, 5, 7, 9, 8. How did you get out there? That 8 should be in here. 1, 3, 5, 7, 9, and 11. They should all be considered to be not A. So how do we use these Venn diagrams for probability? Well, here I have another illustration of the probability of an ordinary die being rolled. So the sample space is this universal set, 1, 2, 3, 4, 5, 6. That's illustrated by everything inside of this rectangle U. If I want to represent the event A, so this A denotes the event, as a number less than 3, then there are 2 outcomes that satisfy this event. That's why they're inside of the circle. So there is a subset of the event A that is the values just 1 and 2. So those are the only values in my event A that exist to satisfy this condition. So the Venn diagram alongside this, so that's this, is the illustration of the event A within the universal set U. Some other notation pieces that are important here is that I can write the number of sample, or the number of elements in the sample space U equals 6, and I'll write that here, number of elements in U, that's equal to 6, so there are 6 values that could appear on the die, and the number of elements in event A equals 2, that's 1 and a 2. So the probability of the event A occurring is the number of events of A divided by the number of elements, the number of elements in A divided by the number of elements in U, which is 2 out of 6, which is equal to 1/3. So that part isn't really any different than calculating any other probability. We can just use this notation here, where P of A means the probability of A, and N of A means the number of elements in A. Just some other notational pieces. We can talk about what we call set notation. If you see this X epsilon A, that is read as X is in A, and literally means is an element of the set A. So in the previous example, we could say that 1 is an element of the set A, or 1 is in the set A. Other things, N of A reads the number of elements in set A, and similarly and comparatively, N of not A reads the number of elements not in set A. So that's some other ways we can illustrate those ideas pretty efficiently. Some other things to keep in mind is how do we just draw these different sort of interactions in these Venn diagrams. So here is a Venn diagram, sample space U, event A, event B, and I want to focus on this shaded area, and we call it the intersection of A and B. And we would write the intersection with this fancy notation that kind of looks like an upside down U. This is read as A intersected with B. And that should make sense, since in this Venn diagram, that is where these two circles intersect and overlap with each other. You might also read this as A and B. And the and is really important here because in the world of probability, and means that they both occur. It's not an either or, it's only where they both occur. Another way of saying this is that A intersected with B is equal to X, where X is in set A and X is in set B. So that's kind of how you can see this set notation with these Venn diagrams. So again, it's the intersection of sets A and B. It contains all common elements in both sets. So this right here. Similarly, we have this other shaded area. Everything that's shaded inside of both circles is called the union. You might see the phrase or the word or show up with this. And this is, the symbol here is not the upside down U, but it's the actual U. And this is a little bit convenient because it's called a union and the symbol looks like a U. So we would say the union of A and B or you might just hear me say A or B. And in this case, or means that any one of these events can occur in order for the entire event to succeed, or the entire probability, event to succeed. So if I say A or B must be true, then that means that anything inside of either of these circles, or where they intersect, is true. As long as it happens inside of these circles, that A or B is considered an occurrence of that event. A or B, or the union of A and B, is given as X, where X is an element of A, or X is an element of B, or X is an element of A and B. So that's just to say that there's nothing different or special about the intersection. All that stuff in the shading is considered part of the union A and B. So just like I said, denotes the union of those sets. The set of all elements belong to A or B, or both A and B. One final piece here is the set notation with a disjoint set. We call this a disjoint set in the Venn diagrams because there are no common elements whatsoever. Nothing is in common between these two. We still have a sample space U, we still have a set A and a set B, but there's nothing in common. We say the intersection of these two is the null set or the empty set, and it's literally this circle with a slash in it. There is nothing that exists that is intersected between those two things. And if this happens, we say that A and B are mutually exclusive, meaning that they don't include the other whatsoever. They are very exclusive, like Mean Girls style. No way, Jose. Are any of these items in each element or each set available or existing within any of the other ones? So let me show you what an example of that might be. If I had a set of cards and I said that here were all the aces, so this would be ace of spade, ace of clubs, ace of diamonds, and ace of hearts, and that could be like event A, and event B could be king of clubs, king of diamonds, king of hearts, king of spades. These are mutually exclusive events if I were to draw from a set of these cards. There's no way that one of these items will exist within the other. So that's what I mean by a disjoint set. So there's a whole lot of notation, there's a whole lot of introduction to this Venn diagram structure, and in the next video we'll start to actually dig into some examples and see how these things carry out.